means I'm going to say the eigenvalue, obviously when I'm going to equate this to 0, I'm going to say that x equal to 1 is the eigenvalue and x equal to 2 is the eigenvalue. But x equal to 1 has multiplicity 2 and x equal to 2 has multiplicity 3 actually. Okay? So 1 has multiplicity 2 and 2 has multiplicity 3. So similarly, you have this n degree polynomial, but when you rewrite it in such a form, you can have that, okay, mu1, mu2, mu_d are distinct eigenvalues. They are distinct eigenvalues where the mu1 has multiplicity n1 and mu2 has multiplicity n2 and mu_d has multiplicity n_d. We're gonna say that these n1, n2 and n_d are the algebraic multiplicities of mu1, mu2 and mu_d. So here the eigenvalue 1 has algebraic multiplicity 2, here the eigenvalue 1 has algebraic multiplicity 2 and eigenvalue 2 has algebraic multiplicity 3 actually. So let me put a formal definition of algebraic multiplicity. So if mu1, mu2, mu_d, you have to keep one thing in head. N by n matrix does not necessarily always have n distinct eigenvalues. It can have, because it can have at most n eigenvalues, but it doesn't mean that it's going to be always having exactly n eigenvalues. Okay? It can have one eigenvalue, is gonna must have one eigenvalue at least, okay, because we also proved it. And at most it can have n eigenvalues. Okay? So imagine that these are the d distinct eigenvalues, values of A. And imagine the PA of x, okay, the characteristic polynomial of the matrix A looks like this actually. Okay? It looks like this. Okay, let's call this star. Let's give it a name star. And let PA of x looks like star. Then n1 are, n1 is algebraic multiplicity of mu1, and similarly ND is algebraic multiplicity of mu_d. Okay? So if an eigenvalue, if a factor repeats some number of times, that number, that power is the algebraic multiplicity of that given matrix. Okay? Next, I would like to answer a question, a simple question, and then we'll move towards some more properties of characteristic polynomial. I would like to move towards a question. What is that question? The question is, what is the relation between eigenvalues of matrix A, A transpose, we know that they have the same eigenvalues, A conjugate, okay, and say A conjugate. Okay, what is the relationship between the eigenvalues of matrix A, A transpose, its conjugate transpose, and its conjugate? So here is a little theorem which is going to list all of these things. 1, lambda 2, lambda n. Okay, they are eigenvalues of A. Eigenvalues of matrix A. Then the same are the eigenvalues A transpose. Secondly, the conjugates of the eigenvalues lambda 1, lambda 2, lambda n bar are eigenvalues, okay, of conjugate transpose and conjugate. In other words, if you have the eigenvalues of A, then what are the eigenvalues of conjugate or its conjugate transpose? Simply take the conjugates of the eigenvalues of A, and that would be the eigenvalues of A. And C is so if lambda has algebraic if lambda is eigenvalue of A with multiplicity, algebraic multiplicity K, then lambda conjugate is eigenvalue of A transpose and A conjugate, and it has multiplicity, has also multiplicity K. Okay, so in other words, if lambda has multiplicity K, then lambda conjugate also has multiplicity K actually. Okay, it has the both multiplicities here. So let's quickly go through the proof of it, and then let's go towards another some of the interesting results about the characteristic polynomial. So what would be the proof of A? The proof of A is going to be, okay, if you take, for example, if you compute, for example, the characteristic polynomial of A transpose is going to be what? Is going to be the determinant of x minus xi minus A transpose, but the xi minus A transpose is same as xi minus A whole transpose. Okay, we saw it previously, and we know the determinant of a matrix and its transpose, they are always equal. So this is same as the determinant of xi minus A. So this is same as the polynomial of the A actually. So this calculation shows that A and A transpose has same polynomial, and hence gonna have the same eigenvalues. How about conjugate? So it's going to be the determinant of xi minus A conjugate, but this is same as determinant of xi minus A whole conjugate, but we need to put a conjugate here actually. Okay, this is what that you're going to get, and this is same as what is the relationship between the determinant of the conjugate of the matrix? Okay, in other words, we know the property that the determinant of the conjugate of a matrix is same as the conjugate of the determinant actually. So in other words, you compute conjugate first and then do the determinant, or you do the determinant and then compute conjugate, it doesn't make any difference. So hence I can say that this is same as determinant of x conjugate I minus a whole conjugate, and which is same as what? Which is same as PA, okay, the polynomial of the matrix A evaluated at x bar, okay, and a whole bar. We're going to compute this, what we're going to get. So A has these eigenvalues lambda 1, lambda 2, lambda n. So this polynomial can explicitly written as x minus or x bar minus lambda 1, x bar minus lambda 2 up to x bar minus lambda n, and conjugate on entire thing. Now what would be this conjugate? So this is going to be x conjugate minus lambda 1 conjugate, x conjugate minus lambda 2 conjugate, so on and so forth, and x conjugate minus lambda n and whole conjugate. And when you're going to compute this, you're going to get x minus lambda 1 conjugate, x minus lambda 2 conjugate up to x minus lambda n conjugate, because the conjugate of the difference is the difference of conjugates. So the conjugate of x conjugate would be x, and minus lambda 1 conjugate, and so on and so forth. So hence, by this manner we computed explicitly the characteristic polynomial of the conjugate of A, because once you have this, so we computed the characteristic polynomial of the conjugate A, which shows like this. And if this is the characteristic polynomial of the conjugate matrix A, then lambda 1 conjugate, lambda 2 conjugate up to lambda n conjugate are the eigenvalues of the matrix A conjugate, actually as elect. You know, it is easy to deduce that since A star is the conjugate transpose, okay, and we know from here that the characteristic polynomial of any matrix is same as the characteristic polynomial of its transpose. So I can say that when you compute the characteristic polynomial of A star, it's gonna be same as the characteristic polynomial of A conjugate transpose, but its characteristic polynomial is going to be equal to the conjugate, so it's going to be the characteristic polynomial of A conjugate transpose, which is same as the characteristic polynomial of A conjugate of x. Okay, because a matrix and its transpose have the same conjugate. So this means that the characteristic polynomial of the A star is equal to the characteristic polynomial of A conjugate, which is this. So if lambda 1 bar, lambda 2, and lambda n bar are the eigenvalue of A conjugate, they are also eigenvalues of A star. So here's a little theorem which says let A be n by n matrix. And let's assume that the spectrum of A is lambda 1, lambda 2, lambda n. In other words, these are the eigenvalues of the matrix A. Then, if you want to compute the trace of the matrix A, then you can compute it very easily by simply summing up the eigenvalues. Sum up the eigenvalues of the matrix A, this is always same as the trace of the matrix A. And the determinant of that matrix A whose eigenvalues are known to you is simply the product of the eigenvalues. Okay? It's the product of the eigenvalues. So, what is the interesting benefit of this theorem? If for a matrix you know eigenvalues, okay, it's a complicated kind of a matrix for which, for example, you know the eigenvalues, then it's easy to calculate its trace. It's the sum of eigenvalues. It's easy to calculate its determinant. It's the product of the eigenvalues actually. Okay? Product of the eigenvalues. Why this is the case? What is going to be the characteristic polynomial of A? You know, if these are the eigenvalues, there's going to be z minus lambda 1, or maybe x minus lambda 1, x minus lambda 2, and so on and so forth, x minus lambda n. Let's expand this. Let's multiply these terms. I'm not going to all multiply all, but I'm going to multiply some terms. So the first term is going to be that, okay, take this x and multiply with the first x, in other words, multiply the first terms of each bracket actually. So what you're going to get? You're going to get x power n. Okay? You're going to get x power n. Then take x, or what are going to be the coefficient of x power n minus 1 actually. Now take, say, lambda 1 from this bracket, and from the rest of the bracket take x's actually. So from n minus 1 bracket I am taking x, and from the first bracket I am taking lambda 1. So what term would appear? So it's going to be minus lambda 1 x power n minus 1. Okay? This is what that you're going to get. Now do the same with the second actually. From the second term take lambda 2, and from all of the rest terms take x actually. So you're going to get x power, because there are n minus 1 brackets rest. So they are going to be x power n minus 1. In other words, all other brackets take x, and from this second bracket take lambda 2. Okay? So the term that you're going to get is minus lambda 2 x power n minus 1, and so on and so forth. And from last I can take what do you call lambda n, and from the all first n minus 1 brackets I am taking x. So the last term that is going to get is going to be lambda n times x power n minus 1, plus so on and so forth. This is just one way. So I'm just keeping the track of the few terms. What would be the last term actually? What would be the last term in this product? So the last term is going to be that, okay, take the lambdas from each term and multiply them together actually. So how many terms are these? So it's going to be, these are n terms, and there is a minus actually. So I can write this as plus minus 1 power n times lambda 1, lambda 2 up to lambda n. Okay? Lambda 1, lambda 2 up to lambda n. From each bracket I am taking lambdas and multiply them, minus lambdas and multiply them. So there are n minus lambda, so therefore it's going to be minus 1 power n, and multiplied by lambda 1, lambda 2, lambda n. So again, first from each term I took x, so I got x power n. Then from the first term I took lambda 1, and from the rest of the terms I took x, so I get lambda 1 x power n minus 1. And then from the second bracket I took lambda 2, negative lambda 2, and from all other I took x actually. So I'm going to get minus lambda 2 x power n minus 1, and so on and so forth. There are going to be for sure more terms, but I am interested in proving this identity, which is going to give us like that. So I can rewrite this as x power n minus lambda 1 plus lambda 2 plus lambda n power x power n minus 1 plus so on and so forth. There are going to be other terms, but the last term is going to be minus 1 power n, lambda 1, lambda 2, up to lambda n. Okay, that's how this expansion is going to look like. Now we also know, in the beginning of this discussion, we also know that for the matrix A, okay, the generic form goes like this: x power n minus cn minus 1, x power n minus 1, so on and so forth, plus c naught actually. And you remember what was c naught? C naught was minus 1 power n determinant of the matrix A. Determinant of the matrix A. And Cn minus 1 is lambda 1 plus lambda 2 up to minus lambda 1, lambda 2 plus lambda n actually. This is what really is the Cn minus 1. Now if I compare this Cn minus 1, so if these both polynomials are representing the same thing, no, the Cn minus 1 is the trace actually. The Cn minus 1 is the minus trace of A. Okay? Now if these both polynomials are representing the same thing, that means this coefficient should be Cn minus 1 and this term should be C naught actually. Okay, this should be C naught. So what does this show? This shows, if I compare this term with this term, so this means that determinant of A is this lambda 1 up to lambda n. And if I compare this term with this term, that means that the trace of the matrix A is really the sum of the eigenvalues. So this proves this interesting basic theorem actually. Okay, proves this interesting basic theorem. Now I am interested in proving a result which is called the Cayley-Hamilton theorem. Okay, it's called the Cayley-Hamilton theorem, and the Cayley-Hamilton theorem says so let's prove the Cayley-Hamilton theorem, that it says that if for a given characteristic polynomial of a matrix, if in that polynomial, if you substitute A, then the characteristic polynomial is going to annihilate the matrix A actually. So it's an annihilating polynomial for the matrix A. Okay? In other words, every matrix is every characteristic polynomial is an annihilating polynomial for the same matrix actually. Okay? It's the annihilating polynomial for the same matrix. So this is what is the Cayley-Hamilton theorem. Cayley-Hamilton theorem says that every matrix satisfies its own characteristic polynomial. Okay? So the theorem goes like this: let A be an n by n matrix and PA of x be its characteristic polynomial. Okay? Characteristic polynomial. Then, if you evaluate the characteristic polynomial at the matrix A, you're going to get 0. In other words, the characteristic polynomial is an annihilating polynomial for the matrix itself.